So we are now focusing on open systems now, which are called control volumes. Okay, so your heart can be considered an open system. It has mass or blood coming in and out. If we pick this dotted section as our boundary, right? But if we pick the whole human body, is it open system? No, it's a closed system. Huh? Sometimes. Yeah, I guess sometimes. Yeah. Yeah, mass flow rate in and mass flow rate out, right? I guess you can. Okay. All right. So let's just quickly review mass flow rate. And fluid students, 41, you've already seen this. But for students that have taken it, this is a good review. You haven't seen this in a year. All right. So mass flow rate, we know if we have a tub here, we can look at that rate of water in the tub compared to what's coming in and going out. Okay. What is this right here, actually? What is that classified as? What do these D's mean? Delta or derivatives, yep. So this is some form of a differential equation, right? You're solving for M. So you're going to find an equation. You could find an equation for M as a function of time. We're not going to do that here. Because we're going to assume that it's going to be steady state, meaning whatever comes in must equal what goes out. Okay, so in the not next slide, but the slide after, that term is going to be 0. Okay, so I'll talk about that in a second. All right, but just write this down for right now. This equation highlighted in blue, and then I'm going to show you how mass flow rate is derived. Okay. All right. So where does this mass flow rate come from? Well, if we take a pipe flow and we take a section, this green section, okay, we know that it's surface area. And it has some amount of water or mass at a time t1. All right? What's going to happen to this section of green section over time? It's going to move, just like that, to a new location. Okay? It does, because it's now moved what? Delta X. Yep. Some change. Okay? So this is the distance traveled by the surface area A in a delta T. Okay? So that is mass at time of T1 plus delta T. All right? So I'm just kind of showing you where mass flow rate, that rho AV, comes from. Okay? This is a general idea of you start with this moves down a certain distance in a certain time. And so let's first start with mass, which is rho times volume. Okay? And volume in this case is your area times delta X. It's the area of that cylinder, right? Between the green and the red. So we're going to plug that back in. So we're trying to figure out what mass flow rate really is. Okay? Well, if you know mass is density times volume, we now know volume of this section is from the green to the red, is the area times delta X. And then how do we find mass flow rate? What's the unit? Kilograms per seconds. So you divide by delta T. Okay? Because we want to know how much mass went through that area in a certain time. Can someone tell me what dx over dt is? Velocity. Do you see how we get rho AV? Okay? Very crude kind of idea, but it's kind of important for you guys to just kind of think about this a little bit sometimes, okay? Because sometimes you're doing a project and you want to know where things come from, you can kind of take it one step at a time and go forward, okay? In these problems, you're going to write the first law, which I'm going to show you here in the next slide for open system, which is a little long. Then you're going to write this. conservation of mass, okay, or mass balance for steady flow. And you're going to write summation of m dot n equals summation of m dot out, okay? That's at steady state, meaning the water level in your tub is always going to remain constant, okay? In intermediate fluids, we actually dive a little deeper and we show students how to solve those differential equations for mass in the tub, or they're doing what? You're doing velocity now? So they're actually plotting you're doing it too. I don't know if you've done it yet. But you drop a tennis ball and you can actually plot the velocity as a function of time, okay? So you do that in different classes, but for this one, that's what you're going to start out with. So here, you have two coming in, one goes out. So mass flow rate 1 and 2 equals mass flow rate 3. This is very, very, very important when you start doing like heat exchangers, because typically there's 2 inlets and 2 outlets. So there's a combination of 4, maybe more sometimes. So write that equation down. You're going to use that. This is true for anything that's compressible or incompressible, okay? Because it's rho AV. Rho is your density. So it could come in here at a different temperature, which is going to have a different density, okay? Or a different pressure, okay? Like turbines, they come in at a high pressure, maybe a different temperature, but they shoot out at a different pressure and temperature. Okay, so their energies are going to be different. If you want to just worry about incompressible flow, you can use volumetric flow rate in equals volumetric flow rate out. Typically, for water or liquids, you can use that. Okay. Some cases, though, like if this temperature difference is significant, we kind of know that, okay, the water is slightly compressible based on the vapor dome, so you have to figure out what those could be, okay, and include them in there. You see that okay over there? So this is really like a heat exchanger, the shower, right? Hopefully everyone showers, okay? And you do this hopefully on a daily basis or every other day at least. At least, right? I hope. You have hot water, cold water, and then it shoots out, okay? Hopefully it does. Depends, right?
It kind of changes.
You need to take MEC 241, you two, with me, and we can size pumps at the end to fix your issue, right?
I don't know if the school will fund that.
Maybe. Next semester I can do an independent study. All right.
Fix all the showers.
Fix all the showers. All right, so let's look at developing this first law equation. Here's a random shape. Doesn't matter. We pick a boundary. It's not a cool one, but I wanted to do something weird. Okay. If we look at that boundary, we can look at the change in energy of this over time. Okay, and we'll go through that here in a second, of what that is. What can cross the boundary? Heat. Good. That's actually my next arrow. Yep. What else could go in or out that we did in a closed system? Work. Okay. Yep. And then
fluid energy.
Now, with fluid energy though, you see how I drew these offset?
Yeah.
Because one could come up at a different altitude, because coming in over here, for example, could have a different potential energy. Could come in at a different speed. Okay?
Yep.
So that in, which is green box, which is the green arrow, that's your fluid energy right there. It's internal energy, pressure, velocity, and potential energy. All right, so coming in, say you have water coming in. What is internal energy? What's that based on? Temperature, thank you. So we know this has a temperature coming in. It could have a speed. It could have a different elevation based on our datum, okay? And then it could have a pressure, right? Well, it usually does if it's moving, right? It has a static pressure. And think about pressure as if you have an air compressor and then you push the button, it's all that stored energy being converted to kinetic. So fluid energy has internal velocity, potential, and pressure. Okay. Then you also got that going out. Okay. You see how this is a little bit longer? Well, we're going to see that we can write the first law, but for specific flow conditions or devices, we can cancel a lot of things. So what do we mean if this system, is this system moving in space? No. So there's no kinetic and no potential. And we assume that the temperature within this region stays the same. Okay? So at steady state, whatever comes in must equal what goes out. Okay? So that's the biggest, that's actually easier than a closed system, right? You kind of don't have to worry about that delta U term. It's mostly looking at Q, W, and these. All right, can I go to the next slide? All right. Oh, let's, don't wait to write it. I'll give you the equation to write, okay? So let's look at this. This is actually the first law for an open system. And actually, it's the first law of thermo, okay? We have our energy system, we have Q, we have W, we have our flow energies in minus out. If I look at the circle ones, what's U plus P over rho equal to? H. So we make it in terms of H. See how enthalpy now becomes important? Okay. So this is the one I want you to write. You're going to assume in your assumption steady state all the time. And you're going to write that equation down every single time. Okay? To get in the habit of writing it. So you have Q, you have W, you have your energies in minus your energies out for your fluid. You see how it's in minus out? Well, if you have H1 minus H2 and you're a gas, what's that equal? What's delta H equal to for a gas? Almost. That's delta U. CP. So delta H for a gas, and we'll get that sooner or later, is CP delta T. Okay? Has everyone got that? So with this one and your mass flow, which you've already written, those are going to be your starting points in your homework. If you're ever stuck, you start with these two. Okay? And these two can be used to analyze all of this that's shown here. Okay? You have to split them up, though. You look at the diffuser first. Then you look at the compressor. Then you look at the combustors, the turbine, the nozzle. Okay? And once you look at every one, you could go left to right here and actually figure out the whole performance of a nozzle, which is a cycle. We'll get to that. Okay, that's going to be your final project. You're going to pick a couple cycles, you're going to run through calculations, and you're going to give that to me. Okay? But these two are your biggest things.